Welcome to Shepherd's Gem School. Today, we are exploring the Presidium Gem Tester II, how it works, the science behind it, and whether it belongs in a serious gem lab. In addition to being a certified gemologist, I've led A2LA certification processes and managed certified A2LA 17025 laboratories for billion-dollar corporations such as AkzoNobel, Sherwin-Williams, as well as a classified military contractor dealing with the Army Research Laboratory. A2LA is an independent nonprofit that certifies lab competence and compliance with international standards. In short, it ensures that your lab results are trustworthy. The principle behind the PGT2 and similar types of gem testers dates back to 1546, when Georgius Agricola described thermal properties in De Natura Fossilium. But it wasn't until 1822 that Joseph Fourier gave us the heat equation in Théorie analytique de la chaleur. That cool sensation you get when touching a gem, it isn't just poetic, it's physics. Gems feel cold because they conduct heat away from your skin more slowly than gas or wood. The PGT2 measures this heat transfer, called thermal conductivity, using a simplified model that factors in specific heat capacity, how much heat a gem can store, thermal effusivity, how quickly it exchanges that heat, and thermal inertia, which is the resistance to temperature change. Now, it's important to note that this is influenced by porosity, inclusions, and defects in the crystal matrix. Let's touch on the physics. Delta T divided by dt is the time derivative of the change of measured temperature difference. Calories divided by centimeter squared times the degrees in Celsius times s to the 1/2 power is thermal inertia. E equals the square root of K times P times Cp is thermal effusivity. We don't need to get caught up in those physics formulas. You can research those in any first year college physics text. The important thing to note here is that heat moves directionally, and it moves more easily along one crystal axis than another. A crystal grows in layers, so conductivity varies from the C axis to the A axis. This anisotropy matters when testing gems. The probe in the PGT2 uses a resistive heater. A 22 ohm resistor operating at approximately 2 volts delivers 0.18 watts of heat, or about 0.043 calories per second. A type T thermocouple, which is a copper constant thermocouple, uses the temperature difference between two junctions, and this produces a voltage signal, which the device interprets to estimate thermal conductivity. The PGT2 has serious limitations. Drafts or air conditioning can skew results. Holding stones in warm hands can affect results. Minimum stone size matters. Small stones attenuate thermal waves. There's an equation for that. We won't go into that today. Gauge R&R studies show greater than 30% variability. This is unacceptable for lab-grade analysis. To improve reliability, we suggest the following. First, Calibrate before any use, after approximately 10 stones, and any room temperature change. The heat kicks on, the AC kicks on, needs to be recalibrated. Always use a gem holder. Never test the stones in your bare hands. Validate your calibration before use with known stones. Take at least 3 readings per stone. Maintain a consistent probe angle. You should be 90 degrees to the facet. Replace damaged probe tips. And remember, the PGT2 cannot distinguish between natural versus lab-grown stones. We saw that in our little demonstration at the beginning. Therefore, Shepard's synopsis is that electronic gem testers like the PGT2 are helpful, but not definitive. Proper gem identification requires multiple steps and tests: refractive index, spectroscopy, UV fluorescence, and more. We can use the PGT2 as a preliminary tool, but never a final answer. If you found this helpful, please subscribe for more gem deep dives, tool evaluations, and poetic highlights. If you have any questions, drop them in the comments below, and please always, always stay curious and know that you are loved. Thank you.